Are we having face cam or are we?
Oh, you guys want to see my face? Sorry.
No, are we?
Are we having face what?
Camera. Wait.
Oh yeah.
Yeah, camera.
Here's my face. That's what it looks like. 1 second. Hold on. Let me just make sure I'm the presenter. All right. There we go. Here. There we go. Okay. All right. There's that good-looking man right there. All right. So here's what we got. We're gonna finish off chapter 20. I think that I can cover the rest of it. Do I want to talk about this? Sure, we can. We're gonna talk about this real quick. So we've been talking about electric potential, and one of the nice things is we can actually use this in medicine. And I mean, see, the thing is, not everyone here is going to be an engineer. Not everyone is going to be a physicist that are sitting in my class. You guys actually might go into biology. You guys might go into a different science. But the point that I'm trying to make is that this stuff that you're learning now is totally applicable. For example, if you're going to be a doctor, you're going to have to use this thing called an EKG. Technically, I don't know why it's called an EKG because it's an electrocardiograph. Cardiograph starts with a C, so technically it's supposed to be called a C. But actually, I can tell you exactly why it says EKG. It's because there's a Dutch physicist who used this technique, and his name was, I forgot what it was. They say it down here. It was the Dutch pioneer Itovansens. Wait, there's a kind of pacemaker. Blah, 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 blah. They say it. I forgot why I don't remember.
I thought it would just be like from the universe.
But anyway, what they're reading is they'll put like
Willem Einthoven.
Okay, William Einthoven. I have no idea why.
Einthoven.
Oh, there we go. And that's why it's an EKG.
So it's not just the universal constant?
It's called the German electrocardiogram. Okay.
Oh, I see. Okay, there we go. Electrocardiogram with a K, because them Germans are Germans.
Electro with a K and electro with a K and cardiogram with a K.
There we go. All right. So basically, one of the ways that he did it was he said, okay, we're gonna put one of these monitors on your shoulder and one on the inside of your groin, and then one on the we can actually measure the electrical signals that are going through your body and then translate that into a machine called an EKG, and we can see exactly what your heart looks like. Electric impulses of your heart. So when you see that machine, it goes beep, 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 beep. That's basically the electricity going through your heart. And it's not like they're not sending electricity, they're just measuring the electricity that your heart is pumping out, because our human body is a great conductor. And this is actually really helpful to doctors, because they can take a look at this and say, there's a P wave, a Q wave, an R wave, an S wave, and a T wave. They just kind of named all of these things, and they say, looks like that T wave is inverted. You had a heart attack. They can actually look at that and say, like, this is what they can diagnose. What is going on inside of you? Because in old school days, if you had a heart problem, they would cut you open. But now you got a heart problem. They're going to take a look at this graph and they'll be like, this is what's going on. I don't need to cut you open. We don't need to have open heart surgery just for me to take a peek into what your heart looks like. Are we cool? And I admit to you, I don't know the science behind it. I mean, I know the science behind it, but I don't know how to read an EKG thing. But I can tell you that that's exactly what it's used for. So we talked about this thing called a capacitor, and I didn't really explain to you where a capacitor comes from. Basically, a capacitor, the most simplest version of a capacitor, is it's two plates. And there's a charge on one side of the plate, and there's a charge on the other side of the plate.
Stored in a magnetic field?
And what happens is, because there's a charge, it's kind of like if you have a capacitor. Let me go back to, I don't want to talk about algebra. Let's see. Let me save this real quick.
Do capacitors store electrical current in a magnetic field or an electric field?
Has an electric field. Here, let's read and make sure I don't speak crazy to you. Let's see.
So we could fake an EKG then.
You could. What do you mean you could fake an EKG?
Manipulating, like if you manage to like manipulate the.
Sure. If you like stick your finger in an outlet and have a EKG going off, like let's take a paper clip and stick it inside the outlet and see what happens. The EKG, sure, the EKG would respond differently.
You could like.
Your heart would also respond differently.
We put an insulator in between the little whatever.
Yeah. In fact, actually, you know what? Have you guys ever heard of the religion Scientology? You guys ever hear that?
No.
Okay, all right.
No.
Without getting into too much into it, because like it's well, I'm not going to comment on people's religions, but I think it's a little crazy. It's a religion that Tom Cruise and I don't know, like I know Tom Cruise and John Travolta are really big into this. It was big in Hollywood, and if you guys ever walk around in California, and they have this place called like the Christian Science thing or the Scientology, what they'll do is they'll go in and you read their books and all of that kind of stuff, and they'll give you the free test, and it's like to test whether or not you're a good person or whatever. They'll have like this measurement, and basically they put this little thing on your finger, and they measure like whether or not you were the Messiah or I don't know, something. It's weird. It's a religion that's full of aliens as well. There are actually aliens in Scientology. It's not really based on science, but anyway. Yeah, I'm sure that someone's going to watch this archive and be like, dude, are you kidding me? I'd be like, I'm sorry, this is what I think. But they do this test at the beginning, and they put this thing on your finger, and then it measures, how holy you are or whatever. And there's this name that it gives you. You have this many, like, brownie points. This is how good you are, right? And so what I did was I went in there, and this was when I was at Berkeley at the time. So I went in there, and I did their test and all of that kind of stuff. Let me finish. I did their test, and I figured out that what their test was is it was an EKG meter. They were putting the electric current through my body. So I built a device in the physics lab that actually amped up my electric current when I touched it. So what they would do is they would put. I pretended that my arm was in a cast, so I had like a cast on. And so they put it over here, and they put it on another part of my body since they couldn't put it on the two opposite sides of the fingers. And then when they did the test, I like turned this thing on, and it's basically like this 9-volt battery connected to a few resistors and capacitors. And I turned this thing on, and then like it would feel a little jolt go through me, but then like my electric signal went up, and then they were like, dude, this guy's like the Messiah or something. Like, this guy has like 20,000 brownie points, whereas like John Travolta's not even that cool. And then they were like, this guy's just messing with us. And I was just messing with them. And then eventually I admitted to it. I was just like, you guys, I was just messing with you. I don't feel like this is a very valid test of how holy you are by sending electric current through it. And this was my way of proving to you guys that this sounds a little crazy to me. That's how it's relevant. But anyway, yes, you can mess with an EKG meter. Yes, what's your question? Yes, here's Brendan's up.
Well, how is it relevant to how they... I know it's not like how it's relevant to what you did, but how is it relevant to how using electric to figure out how it's so holy? Like, why?
Why do they use electricity to figure out how holy you are? That's exactly what my point is. I don't think it did make sense. And so... if you ever have a chance to talk to a Christian or a Scientology person, then ask them, because I don't know. I don't understand that about Scientology. But anyway, I'm letting you know because it's big in California and Hollywood, and all these Hollywood movie stars are doing this. So I'm giving you a heads up, not to say that I'm like swaying you into one direction of religion or the other, but I found that when I left Hawaii and went into the mainland, I would have these kinds of discussions with people all the time. And so I'm giving you a warning because most of you guys haven't really lived in Hawaii or outside of Hawaii for a very long period of time. So maybe Victor, you've lived all over the place. But then again, you weren't necessarily old enough to, like have them pull you into Scientology and all that kind of stuff.
To remember stuff, right?
Yeah. So that's what I'm saying. Okay? Because I mean, I'm betting that you guys are probably going to be traveling away from Hawaii for a period of time. So, there's going to be stuff out there. And essentially the Scientology put you on an EKG meter and then measured how holy you were. And I was like, wow, that's interesting. It's not accurate because apparently I'm an angel, a high angel, priest or whatever. Because I touched my battery when I did this test. And they were like, well, this dude's an angel. And I'll be like, no, I am not an alien, nor am I an angel. I just was messing with you guys because this is craziness. Anyway, let's move on.
I'm a cheater.
Yeah, because I'm a cheater. I'm a liar, folks. I'm just letting you know. All right. The way that we can measure a capacitor is we measure it in terms of charge and voltage. Okay? The capacitance that something has is straight up equal, and this is just an equation you guys should write down. Actually, did I finish saving this? I forgot. Uh, 2014 02 07.
Oh, 7.
Today's the 7th day.
It is Friday.
It's crazy. All right. Let me make a new one, and then just write this equation down: Q or C equals Q over V, and we'll talk about that.
Q equals C over V?
Yeah, it's right here. Or C equals Q over V. And it's saying that basically in this expression, Q is the magnitude of the charge on either plate, and V is the voltage difference between them. By definition, the capacitance is always a positive quantity. How do we measure capacitance? What is the units for capacitance? Capacitance is measured in farads. After this dude named Michael Faraday, and he was a English physicist. He's also helped us out with a lot of. No, wait, that was Michelson and Morley. Michael Faraday was, he was an English physicist, but he was also this guy who did a lot of electricity stuff. So it's really cool. So 1 farad is equal to 1 coulomb per volt. So C equals Q over V. Q is the charge. V is the voltage. This is all measured in farads.
What is the equation for voltage again?
Actually, you know what? At this point, we don't really ask you to derive the equation for voltage. We just tell you what the voltage is, or ask you what it is. So you don't really even need to like. All right, fine. We'll take a look. Voltage. What was it again?
Isn't it like J or C? Joules over charge? Or C? J or
Oh
C?
yeah, it's voltage is KQ over R, or KQ over R. The voltage is equal to KQ over R. That's for a point charge, that is.
So what's the V equals J over C?
V equals J over C is the, you're talking about the energy conservation. Here, right? This one right here. The electric field is the voltage divided by the delta S, which is the distance, or W over Q.
Here's we have this. Which one is it?
Oh, joules per coulomb. Yeah, 1 volt is a joule per coulomb. That's the units. That's not the
Oh, okay.
equation. All right. Here, let me do a problem for you, and you guys.
Oh,
kind of
so
be
is
like,
it
oh, okay. I got
delta
it.
V equals negative W over Q naught? Oh, that's the potential.
All right. So you ready? Here, let me do an equation for you. Ready? We have a capacitor. It is 0.75 microfarads. The charge on it is 16 volts. What is the charge on each plate of the capacitor? It's very simple. We just do, all right, if they want, we know the equation is C equals Q over V. They told us the capacitance. I forgot what it was. They told us the voltage, which was 16 volts. The capacitance was what, 1.2 or something like that? It was 0.75 microfarads. 0.75 microfarads. If you want the charge on it, you simply go C times V. Okay, fine. 0.75 times 10 to the negative 6 farads times a 16 volts is equal to, Yes, that is mu f.
Okay.
And by the way, do you understand what I mean by microfarads over here?
Yeah, it's 10 to the negative 6 power.
It's the same thing as times 10 to the negative 6. It's a micro. Means really small. So 0.75 times 16, that's what? 3/4 of 16, which is 12? 12 times 10 to the negative 6. And what is the charge? This is measured in what?
Faraday? No. We use that the Faraday?
Coulombs.
Oh, coulombs. 1 coulomb.
12 times 10 to the negative 6 coulombs. Let's see.
So what is capacitance measured in?
What is capacitance measured in? It's measured in farads. It's a new unit.
What does it?
What does it what?
What does it measure?
It measures, all right, here's the way I think of a capacitance, okay? What's going to happen is, if you have a circuit, right? You have a circuit which is just a wire like this, okay? Then what's going to happen is, and you have a battery in it, and then say you have a switch right here. Here's a switch. So I should probably erase this over here. So when I close this switch, it will short out this battery. It will make a circuit, okay? And then what happens is, when I close this switch, what's going to happen is there's going to be electrons that travel along along the wire. You guys got it?
Mm-hmm.
It's just going to travel along the wire, blah, blah, blah. That's pretty much it. But what a capacitor is, imagine the electrons are traveling along the wire, and this is actually how we represent a capacitor. This is how it looks like when we draw a circuit diagram. Is we actually draw like 2 vertical lines like this, and it's 2 plates, and it's basically 2 plates butted up against each other. Now, what's going to happen over here? Well, what's going to happen is you're going to have all the charges building up on one side over here, right? It's kind of like they're going along, but then they can't get across because there's a gap in between them. So they build up over here. And then eventually what happens is they build up so much that you can release all of this energy, and it makes this jump over. And so that's kind of what your flash bulb is doing. Like when you have a camera flash, your battery will charge up one plate of the capacitor, and then you say, okay, go, and then it releases all this energy, and that's how you have a camera flash. So a capacitor is kind of like the ability to like, your capacitance is measuring how much energy this thing can store per volt.
So besides a camera, what else uses a capacitor to do as such?
A capacitor is used almost everywhere. In almost every single electronic device you have, you're going to have 2 kinds of things. You're going to have a resistor, and you're going to have capacitors. You're also going to have transistors. And those do different things with your electronic devices. A capacitor is used for storing up charge, or it's also used for regulating charge. Like it will, if your computer has a bunch of capacitors in it, and you get a big electric socket into it, that thing will absorb a lot of it, so it won't like burn out all of your sensitive electronics and whatnot. It's also the stuff that they use. They use a giant capacitor in the paddles that they go clear, because they need to build up the energy. And by the way, they're not doing this to build up the energy. They do this to warm up the paddles. But you know, the thing goes. It's kind of like Iron Man's.
Oh, his arc reactor.
Arc reactor shot thing is. That's kind of what he's doing. He's charging it up first.
Oh, that's good.
You guys get it? All right.
Like, yeah, the measure of how much is the potential.
All right.
So how come that is -5, but we still have -6?
Okay. All right. Wait. Let's talk about capacitance a little bit more, and then we'll talk about that. Hold on 1 second. Ready? All right. So a capacitor gets its name from a capacitor its capacity to store both electric charge and energy. So that's what you're measuring, is the amount of its capacity. How able is it to store electric charge? Does that make sense?
Yes.
So that's going to answer your question. To answer Austin's question is, we got 12 times 10 to the -6. They got 1.2 times 10 to the -5, right?
Wait, they just moved it over to 1, right?
Exactly. What they did was they said, okay, your answer is actually we want to put in scientific notation. Scientific notation requires you to have only one digit in front, so it's 1.2
So it's the same exact thing.
times 10 to the negative 5 instead of 12 times 10 to the negative 6.
So it's exactly the same.
Yes,
thing.
they're the same answer.
Okay.
Are we cool?
Yeah.
Yeah.
Okay, good. Good. It's really just one equation. It's a pretty simple equation. Let's talk about a parallel plate capacitor because there's different kinds of capacitors. All right. I like talking about parallel plate capacitors because they're pretty straightforward. Parallel plate capacitors do this. All right, hold on. Let's see. Let's read it a little bit because I forgot what I was going to talk about. I apologize. I usually am a little bit better prepared for that. In particular, a simple capacitor parallel plate resistors. All right, here we go. To begin with positive and negative charge, we found that the electric field is equal to sigma over E naught. Noting the charge per area is sigma Q over A. Okay. So, here's a new equation that I have to introduce to you, and it's not really that bad. Okay. What the question I have for you is what is the electric field of inside of this between this capacitor? If I have two plates, if I have two parallel plates, what is the electric field? All right, and the way you figure that out is this.
Is that the equation to figure it out?
All right, the way you figure it out is this. A capacitor, actually this would be the equation we want to stick with right here. If you want to talk about a parallel plate capacitor, which is the most general kind of capacitor that we're talking about, is it's equal to C equals E naught A over D. And let's talk about what that is.
Over what? E naught over.
Capacitance is equal to E naught C over D.
Is it the same exact C?
Oh, no. It wasn't. It was A over D. Sorry, A over D. That would be a little confusing. And this is talking about a parallel plate capacitor. Okay. So this is the zoomed-in version of what I got here. Its capacity to hold energy. All it's saying is that disregard the E naught for now. Okay. Do you guys understand where the A comes from? The area.
Yeah, because then it's the area between those two.
No, it's not the area between those two. It's the area of the actual capacitor.
Itself.
Yeah. What they're saying is the bigger the capacitors, the bigger the area, the more capacity it has to hold stuff in there.
So if it's a thin one to a thick one.
And the bigger the capacitor, the more ability it has to hold stuff in there. And so it will have a higher capacity. So that's why we have the A in the numerator. Are we cool? Does that make sense?
Mm-hmm.
All right. The D is the distance.
I'm wondering for the A.
If the distance is really big, then that capacitor doesn't actually have a good capacity to hold things because it's going to be hard for the electrons to jump over, right? So if D gets really big, your capacitance gets really small. And if D gets really small, then your capacitance gets really big. Do you understand? The D is the distance.
For the A.
Or I should put separation. All right, question.
For the A,
Yeah.
is it talking about the surface area of this or just the width of it?
No, the surface area as in like if this were height and this were width, then it's width times height.
Okay. So,
The actual area of the capacitor.
Oh, okay.
Does that make sense?
Got it.
The bigger that thing is, the bigger your capacitance is going to be. All right, what is the E naught? The E naught is actually called the permittivity of space. And all it is, my friends, is it's a number that you look up. And I forgot what that number is. Oh, it's this number right here. It's 8 times 8.5 times 10 to the negative 12. Negative 12. That's it. That's what your capacitance is. Or that's what the E naught is. And what that is it's kind of like this constant. It's saying that there's a certain like ability for these electrons to jump if it's jumping over a gap of air. And so that's why we put E naught, because usually we're talking about air in between there.
Is that a universal number?
Does that make sense?
Yeah.
It's not really a universal number, it's a number specific to air, but usually we're talking about air.
So what would the number be?
So it's 8.85 times 10 to the negative 12, and the units for it is Coulomb squared divided by Newton meter squared.
8.85 times 10 to the negative 12.
Yeah, and that's for talking about air.
Permittivity of space.
Permittivity of space.
Permittivity.
Surprised I don't mention that a little earlier.
Yeah.
I think it's because we used that before in a previous chapter, but it's actually kind of a confusing topic. Now, what I mean by that is we found that we can put different things in here, in between these capacitors, to actually make it better. To actually make the capacitor better. We found that what we can do is we can put different kinds of materials in between these parallel plates, and that will actually amp up the capacitance. So we don't need to have just a gap of air in between. We can have, like, maybe put some kind of silicon or tinfoil or something in between. Do you guys get it? Or and how do we get these things so close? Well, how do we actually build capacitors? Here's what capacitors actually look like. You guys see those?
Yeah.
Oh, so the
Yeah.
two plates on the outside and something's in the middle of it?
No. Look. That's what they look like. They look like those little tubes. And you're wondering, like, wait a second. I thought you told me that most capacitors are plates. How are we getting it in little tubes? And why would you get it in little tubes? Well, if you want to get it in full-on plates, it's going to take up a lot of room. So it'd be nice to roll up those plates. So what we do is pretend that this strip of paper right here, this green strip of paper, is my capacitor. Oh, darn, did I hang up? It did.
Welcome to WebEx. Please enter a... Welcome to WebEx. You will now be placed into the conference.
Sorry, I accidentally hung up on you. Anyway, pretend that this green strip of paper is a parallel plate capacitor, okay? Pretend that this green strip of paper is another parallel plate capacitor. Its capacitance depends on a few things. Depends on the area of these things, right? It also depends on the distance in between here. If the distance is small, high capacitance. If the distance is big, low capacitance. If they're touching, it's not a capacitor anymore. We got that?
So if you have a large, a relatively big distance and it's like gigantic capacitors, you still have to have capacitance. Right?
Yeah, I guess if you had these huge plates, like these gigantic plates, but then you had a bigger distance, then yeah, you would still have a relatively high capacitance because the size of the plates balances out with the distance in between them. But here's how we get them close. Instead of taking these things and putting them as close as we can, as close as we possibly can, what we figured out is we can take something else, a different material that's not made of the same material as these capacitors, and we can put it right in between, and then we can put it real close. See, I sandwiched that pink paper in between these two green papers right here.
They're still not touching.
So they're still not touching each other. So I can get them close. That's an advantage. You guys get it? I also found that what I can do is when I put something in here, that doesn't change the value of E naught, but what that does is it can boost my capacitance up depending on the type of material that I put in there. And so that's one way, that's one of the things that we can do to boost up these capacitance. That's how we can make these devices smaller and smaller, is we figure out different materials to put in there. So we take a capacitor and we take another capacitor and we sandwich him in between this thing. You guys see what I'm doing?
Mhm.
But this is still not addressing the fact that these capacitors that I have are flat. Or this capacitor I have is flat. Most capacitors are tubes. So what I'm going to do, and this is how they actually build it, is they take another piece of that material and put it on this side, and then guess what they do?
Roll it up.
They roll it up.
Roll it up.
Exactly. Now, I can't roll this for some reason. There we go.
So those are all different capacitors then?
Yes, these
I
are
thought it
all
was just
different
one whole big
capacitors.
thing to put into the capacitor.
No, these are all different kinds of capacitors. Now look, I have a capacitor that has the size of this big plate rolled up into this small little thing.
So this
And the plates aren't touching each other because I have the material in between protecting them, and also that material in between helps me get those plates really close to each other. So this is what they do with capacitors. So technically this is a parallel plate capacitor, even though it's rolled up. You know what I mean?
Is it the same exact physics or the math that we just did, but now it's rolled up, so it's still the same exact?
It's pretty much the same, yeah. The only thing that changes is, and so what Austin is asking is, well, what is does the math change because I rolled it up as opposed to do this? And I think and the math doesn't change. It's the same exact math, but there is something that did change, and it's because I put a different type of material in here. We found that we found that there's these things called dielectrics, and dielectrics is basically some kind of material. It's the pink stuff that I use to help increase the capacitance. And here's kind of how it works, okay? Say that we have our parallel plate capacitor. Got it? And it has an electric field that goes across like this. Just goes straight. Got it? Here's the E field. And what I'm going to do is I'm going to put in some kind of material. And that material usually looks like this. It's got these dipoles in it where there's this positive and negative. Like this. Are we cool?
They're both positive and negatives.
Yeah, and they're just kind of in there. The molecules are in there that are kind of like just hanging out together. Right? Because they're attracted to each other, right? But they're randomly all in there. They're not really like, they're just kind of like plus minus over here and then a minus plus. As long as they're together, they're fine. Cool?
Mm-hmm.
But when I put this material now inside of my capacitor, so I'm putting it in here now, what's going to happen is all of those things are going to start to align. Like this. All of those things will be aligned with the electric field. Does that make sense?
Yeah.
Yeah.
And then what happens is, because I put that stuff that align with the electric field, it actually amps up my capacitance. It makes the capacitance like super big. And so the new equation now is C is equal to, what do we have? We had E naught A over D. We also have this K, and it's not a full-on K, it's actually a kappa. Looks like a capital K, but just, small, like a lowercase size, but capital K.
Okay.
And it's called the dielectric constant.
We have too many K's in that.
Yeah, I know. There's also way too many X's and E's and A's. We actually ran out of letters at some point. So this is this equation right here. This one's actually a cool equation. It's pretty straightforward. Let me show you how to use it.
We need to create a table of dots.
Yeah, to keep track of all these things. All right,
Like spread all over the book.
well, let's try this one. Okay, even more charge up. A parallel plate capacitor has a small this area and a small separation. The spacing between the thing is filled up with a dielectric constant. The capacitor is connected to a 12-volt battery and has a magnitude charge of blah 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 coulombs. What's the value of the dielectric constant K? Okay, fine. That's a lot of stuff, so I'm going to make this thing small so I can see it. I'm going to take this thing, I'm going to make it small so I can see it. I'm going to make that thing small. I'm going to read off the problem that we have here. Alright, fine. Okay, you guys ready? Here we go. Parallel plate capacitor. Looks like this. Got it? And it looks like this. And it's connected to a 12-volt battery. Positive, negative on this side. So what happens is the positive charges will build up over here. The negative charges will start to build up over here. And after the charge is built up enough, we're allowing them to jump ship. They can go from one side to the other. Because the positive charges are going to start to be repelled by this positive wire, and this negative charges are going to start to be, well, not repelled. Well, yeah, repelled by this negative wire, but essentially this positive charge is going to be like, that other plate looks really good because it's got a bunch of honeys that I like. And what I mean by honeys is oppositely charged, things. And I'm a positive, they're negative, I like that. Right? So they're going to jump ship. We found that jumping ship will actually amp up if we put some kind of material in here that has a dielectric constant of K. We don't know what K is in this particular case, so we're going to try to figure that out. We know that the voltage is a 12-volt battery. We know that the charge on each plate is 3.62 times 10 to the negative 8 coulombs. We also know the area of each thing is 0.0280 meters squared, and we know the distance is equal to 550. Does that say 550 or 0.55? I don't know, it looks like 550. I'm going to put 550 times 10 to the negative 3 meters.
I think that's 0.5550. 550.
All right.
Mm.
Yeah, I agree. So I'm going to put 0.550 times 10 to the negative 3 meters. You understand why I didn't put millimeters, but instead I put meters times 10 to the negative 3? It's because when I multiply all of these numbers together, I want to use the same units. So I'm going to use the units of meters and that kind of stuff. I don't want to mix in millimeters, so I'm going to throw in that scientific notation.
So,
we cool?
So, when the positive charges are on that indicates that electricity is flowing, even though the circuit is not closed?
No, the circuit, well, the circuit is not closed. I guess you're right. There is technically a gap in the circuit. There's a break in the circuit. But we're putting that break over a really big area and a very small distance. So it's charging up, and as it charges up, it's going to charge up, and then it's basically going to go, boom, it's going to go. Okay?
How does it charge
And
up?
the distance is so small, so
Not,
I measured that right.
What is that? After it's done charging up.
to charge up.
Yeah, after it's given time to charge up. We cool?
How does it charge up?
Oh, it charges because your things are going to start to flow. Your electrons are going to start to flow, and they're going to go over here, and then they won't be able to make it to the other end.
So electrons flow.
What is that?
So electrons flow even though they're not connected.
Yeah. Well, they're flowing because they're being pushed by this battery. When you connect it to the battery, it's pushing those electrons there. If you have a circuit and you just don't have a battery, those things aren't going to move. The electrons aren't going to move. You get it?
So the battery pushes.
It's the battery that's doing the pushing.
And you don't necessarily need to have a closed circuit for the battery to push.
Yeah, the battery can push, and if you break the circuit, like say I have a wire like this, and I have a battery, and I connect it to the battery. Here's a battery, okay? And then say I put a light bulb over here. We're talking about a Christmas light. We're actually talking about a new type of thing called a resistor, but whatever. Say that electrons will flow through this thing right here, and then it will cause the light bulb to be bright. Got it? If I put on a full-on gap in between here, like I cut out this whole section right here, then the electrons are still going to try to flow, but then they're going to be stuck right over there. So we kind of came up with this cool thing where we said, all right, let's let them get stuck over here, but I'm going to let the area of the thing that they get stuck on to be really big. And then I'm going to let the area of the thing that will receive them, the catcher's mitts, be really big as well. And I'm going to put these things very close together. That's what a capacitor is. Even though technically there is a break in your circuit, the break is so small and the area that they're building up on is so big that they'll be able to make that transfer over. You guys get it?
So at this point right here, since they're not charged, they can't make it yet until
right.
they're charged.
You have to, but if you take out the battery, then nothing flows.
Yeah.
And
the lifeline.
and yeah, the battery is what pushes everything along. So there's no point in not having a battery. It's the battery that pushes.
Electricity flows even though the battery, even though it was breaking.
Electricity will flow even though they're breaking the circuit. It might not flow across the gap, across the break that you made, but it will flow up until that point, and then it won't. Like maybe it might not jump that gap. Although if it's enough electricity, sure, it will jump that gap right over. In fact, that's what lightning is.
I mean, not talking about capacitors.
You're not talking about what?
If we're not talking about capacitors, if you just broke the circuit, it would still flow.
It wouldn't flow through the circuit because there's a break in the circuit.
Stop.
It would stop.
Yeah, it would flow to the
end of it.
Flow as far as it could.
That's a good question. No, because technically it wouldn't really flow at that point. It would just kind of build up, and then it would well, we're not going anywhere, so it wouldn't really be able to flow.
Would it dissipate?
Basically, you just broke your circuit, and then it's kind of like having a battery, just like a straight up battery. Let's have a battery out in the open. You know what I mean? We have a positive lead and a negative lead on the battery. We're talking about a 9-volt battery. You guys seen 9-volt batteries, right?
Yeah.
There's a positive side, there's a negative side. Electricity doesn't flow in between here. The battery's not connected to anything, and the reason being is because they made that gap big enough for electricity not to flow there. Right? Now, if you took 2 wires and connected them, 9-volt battery, took 2 wires and I just put them out like that, the electricity is still not going to flow. But if I put them close enough and I made them charge up plates that were big enough, then it could short the circuit. It could make that jump.
Without the plates, why would having the plates make it come together?
Because what you're doing is you're allowing the electrons to kind of like build up on this place. You're allowing
So you're saying that even without the plates, they would still build up on the wire.
Yeah, but it won't be big enough to jump. So it won't. At that point, it won't really build up on the wire.
Okay, so it will still build up on the wire.
Yeah. Okay, fine. It will build up on the wire, but it won't be big enough to jump.
Would it be big enough to power anything?
In order to power something, you might want to connect those 2 wires to something.
Yeah.
So that's what we're gonna do.
Thing.
Right. If you just have 2 wires that are just like antenna going out and they're not really connecting anything, then no, it won't really.
But if we connect one side to a light bulb, doesn't the fact that power is still flowing, building up in there?
Well, no, you need to have that thing go somewhere. So if you have this, if I have my battery and I have a light bulb, and then that's it.
But it needs to go somewhere else. Yeah.
It needs to complete the circuit. You can't have that and then your battery is turned on. You have to have the thing go through the light bulb and come into the negative side or come into the other side, and that's what will complete your circuit. I see what you're saying though, because a capacitor is technically a break in the circuit. right?
Yeah.
Yeah, no, I see what you're saying. But the thing is, we're making that break so small, and we're giving it a bigger area to start building up its.
I know, it's virtually nothing.
That it's well, it's not that it's virtually nothing. Is sometimes we want these charges to like not just go continuously, but say that we want it to like have a really big spike of charges go through at one time, but we want to so what we'll do is instead of having, I guess here's one way to think about this. If you want to get somebody wet, right? And you have a roof over here, okay? And you have like little drops of water coming down. And that's what happened. There's like just water just kind of trickling over there. You could have them stand underneath there, and then the little drops of water would fall on their head and, whatever, right? Or what I would do, because I'm a punk, is I would block that water somehow. Got it? And then what I would do is that water would kind of trickle and it would stop flowing. But it will build up. Now I got a big bucket of water, or a big barrel of water, and then I would break that block all at one time, and then all that water would rush through the system, making that guy wet. That's the way I would do it. That's the prank I would play.
Don't they do that? Or like some places where they have it starts filling up and then it's getting to it and then it hits and then it's huge water.
Yeah, so that's kind of exactly what's happening with a capacitor is your electrons will go, and you can either have them go across small but continuously, or you can have them build up and then just go one time, and then there you get a flash of a light bulb, a flash bulb. You know what I mean? It flashes. It all of that energy just goes real quick. And these things don't charge up very slowly. They charge up pretty fast. Anyway, let's go on to the problem at hand. Are we cool with that?
Did I solve for K correctly?
Yeah, essentially. Yeah. All right, so we can figure out the capacitance using the Q and the V. They actually already gave it to us straight, right?
Mm-hmm.
And then you plug it in, you can get an answer, whoop-de-doo, whatever. We also know that there's another equation for capacitance, and it's particularly talking about parallel plate capacitors, and it's E naught A over D. But since they're telling us that they're put in a dielectric, so it's K E naught A over D. If there were no dielectric in there, and if there was just air inside or just space, it would be E naught A over D. But in this case, it's K E naught A over D. Are we cool?
So we're just solving for K.
So, well, it's the same capacitor. So it's K E naught A over D times Q over V. We just solved for K. Yeah, exactly. So it's K equals D or QD over E naught AV. Are we cool? And we just plug in our numbers, and that's our answer.
I'm not remember any of this.
What is that?
I'm not going to remember any of these.
Just write down this equation and write down this equation. And to be honest with you, dude, like, I'm a physics major, and I kind of remember these equations. These particular equations, I don't remember, like, off the top of my head. I don't know them as well as I know mechanics equations. And the reason being is because I'm not really this is like what you would use every day if you're an electrical engineer. Give me a second. There's a important phone call that I might need to take. It might be the, hold on 1 second. Hello? Oh, NJ.
Mission time.
Oh, Ginger, what's going on? You're actually here. I'm actually in class right now, so I can't talk for very long, but let me tell you, your boys are getting an 84 and an 86%. They are already caught up. They've got a B. They were answering all the questions I was asking them. They were killing it in math. So when you're asking me, are they caught up or can they catch up? Yes, and they've already caught up. If they keep on the same track that they're doing, they're going to be on the path to being some of the best students I've had in my class. Okay? So I got to go. I'm finishing out teaching class, but that's what I have to say about the long twists. But keep them coming in because I think it's really helping them. Actually, I thought they left already. They said they were. They told me they were supposed to leave at 11. All right. Okay. Bye. All right. I'm sorry. There was a parent trying to call me, but yeah.
So C could be the same thing as Q over V, right?
Well, C is Q over V. C
So
equals
instead
Q.
it could be something like QD over E naught AV.
Well, that's what I have.
Oh.
That's what the answer is.
So this wouldn't work.
No, that totally would work. You would just have to figure out what C is first.
And it's Q over. Okay, got it.
Yeah. All right. And then the rest of it is really just talking about more dielectrics and that kind of stuff. But that's it. That's the end of chapter 20. We really wanted to talk to you about like energy and energy storage and how do we store energy and all of that kind of stuff. We cool?
But everybody loves that, right?
Well, look, to be honest with you, chapter 20 I feel like is the not fun stuff. This stuff was not fun. When we hit the stuff next week, I feel like that's going to be, to me, it's going to be a lot more fun. There's going to be stuff that we're going to be like, I understand that now. But we kind of had to get
I
through
think I
this
like more of a practical science, not so much math science.
Well, no, but this is a practical science. I just need to make sure that you have the understanding of a capacitor down before I start introducing you to circuits that have both resistors and capacitors in there. You're going to ask me, well, what the heck is that doing there? And I'll be like, well, this is kind of what's going on with that. Are we cool? And I'll tell you what, I'm only going to ask you to calculate these things a few times. And then after that, it's not that I'm going to ask you not to do that later. We're just going to, like, I want to make sure you know this equation so you can calculate this. But this isn't as fundamental to me as, like, knowing how to break up a vector into their components. Like, that's fundamental. That you need. We cool?
Mm-hmm.
So, I mean, you can kind of tell that when I'm lecturing on this, I'm a little shaky on it myself. I kind of like, what is that again? I don't remember that and that kind of stuff. It's because I know the equations, and I don't memorize all the equations. In fact, as a physicist, I hate memorizing any equations. I like deriving things. But there's some things that you can't derive. You just got to know the equation. And in that case, I'll look it up in a book. That's what I'll do. We cool?
Mm-hmm.
All right, so that's homework. I'm going to assign Chapter 20 homework today since we finished talking about Chapter 20, and we will be good. Tomorrow, or on Wednesday, we're going to start up talking about other stuff, and I'm going to give you your grades now. And just to let you know, just to give you guys a heads up, even if you guys haven't turned in stuff just yet, I'm still going to get you guys a passing grade because I feel like you guys are catching up to it. I just had a problem with putting up the drop boxes a little late. We cool? So I'm not going to like burn everyone and give them Fs because, you know. But I do want you to get your assignments in on time.
Alright.
What is that? Technically, everything from Chapter 19 was due today.
So yeah, I know that, but when do you want like
When do you want Chapter 20 stuff due? I'll try to make sure I assign it this weekend.
I mean, because I don't work well under a deadline.
Okay. I'll try. What do you guys say to having this due in a week? Is that enough time? So I'll try to assign it by Monday, and it will be due next week, Monday. So you'll have the assignments posted by this coming Monday, and then the following Monday you'll have it due. Does that sound good?
Okay.
All right.
Okay.
All right, and I won't. I would say maybe I'm gonna limit it to about less than 10, definitely, maybe more than 5. But I'll choose the problems that are straightforward and stuff that I know that we covered in class. Okay.
Yeah.
All right. Talk to you later. See most of you at what you call it at